Welcome to AI, from Zero to Researcher. This is a series that takes you from knowing nothing about artificial intelligence to understanding how the field actually works. Not the hype, not the buzzwords, but the real ideas. Every episode builds on the last. No prerequisites beyond curiosity. Today, Episode 1. What does it mean for a machine to learn? Imagine you need to build a spam filter. You sit down and start writing rules. If the subject contains free money, mark it as spam. If the sender is unknown and the email has a link, mark it as spam. You write 10 rules. Then 50. Then 200. Spammers change one word and your rules break. You write more rules. It never ends. Now imagine a completely different approach. Instead of writing rules, you hand the computer 10,000 emails, some spam, some not, and say, figure it out. It looks at the data and finds patterns you never thought of. It builds its own filter. That second approach is machine learning. But what does figure it out actually mean? That's not a poetic question. It has a precise mathematical answer. And by the end of this episode, you'll know it. This is Episode 1, No Prior Knowledge Needed. Everything we define today will be used in every future episode, so if something feels unclear, pause and replay. These definitions are the foundation. Let's start with a distinction. Most introductions skip. Artificial intelligence is the broad goal. Build systems that do tasks we associate with intelligence, recognizing faces, translating languages, planning moves in a game. It's a goal, not a technique. Machine learning is one way to pursue that goal. Instead of a human writing every rule, we let a system learn patterns from data. That's the key shift. Rules come from data, not from a programmer's head. Deep learning is a subset of machine learning that uses multi-layer neural networks. We'll get to those in Episode 3. For now, just know the nesting. AI is the field, ML is the approach, deep learning is one family of models within ML. Back to our spam filter. In ML terms, the email is the input. Spam, or not spam, is the output. The thing in the middle, the system that maps input to output, is the model. And the 10,000 labeled emails? That's the data. Now here's the most important definition in this entire series. Pay attention. A model is a parameterized function from inputs to outputs. It takes something in, transforms it according to internal numbers called parameters, and produces something out. Those parameters are what make one model different from another, even if they have the same structure. If you remember one sentence from today, a model is a parameterized function from inputs to outputs. That definition gives us 4 pieces that researchers always specify. Task: what are we trying to predict or generate? Data: what examples do we have? Model: what family of functions are we allowing? Objective: how do we measure good versus bad? Every paper, every experiment, every claim in AI comes back to these 4. If someone can't tell you all 4, their claim is incomplete. So what does learning actually mean? Not that the model becomes alive, not that it gains awareness. It means we adjust the parameters so that the model's outputs get closer to the desired outputs as measured by the objective. That's it. Learning is parameter adjustment driven by data. One distinction worth planting now: not all numbers in a machine learning system are learned from data. The weight W in our model, that's a parameter. The model adjusts it during training. But choices like how fast to adjust, the learning rate, how many examples to show at once, the batch size, or how many layers to use, Those are set by the researcher before training starts. They're called hyperparameters. Parameters are inside the model. Hyperparameters are outside it. They control how training works. You will encounter this distinction in every episode from here on. When a paper says, "We tuned hyperparameters," they mean they tried different researcher-chosen settings. When they say, "The model learned," they mean the parameters changed. Two phases that beginners often mix up. Training. The model sees many examples, measures its errors, and updates its parameters. This is expensive. It's where learning happens. Inference. Training is over. Parameters are locked. We feed the model a new input and get a prediction. When you ask a chatbot a question, that's inference, not training. This distinction will matter a lot in episode 10 when we talk about language models that seem to learn during a conversation. Spoiler, they usually aren't. They're using information from your prompt during inference, not updating their weights. Let's make this concrete with the simplest possible model. We have data. When x is 1, y should be 2. When x is 2, y should be 4. And so on. Our model is one multiplication. Prediction equals w times x. Just one parameter, w. The question is, what value of w makes the predictions match the data? With w equal to 1, every prediction just equals the input. All too low compared to the actual outputs. With w equal to 3, we overshoot. Every prediction is too high. Somewhere between 1 and 3, there's a value of w that fits best. And there it is. W equal to 2. Predictions match perfectly. Zero error. The model learned that w equal to 2 is the right parameter for this data. We can even plot this. For every possible value of w, compute the total error. You get a curve, and the best w sits at the bottom. Training is just finding the bottom of this curve. For our toy example, you can see the answer by eye. But real models have millions of parameters. You can't try every combination. You need a smarter way to find the bottom. That's what episode 4 will teach. Let's see this running in actual code. Nothing fancy, just Python and basic math. Look at that. The error drops steeply, hits 0 at w equals 2 and climbs back up. This is the curve we animated earlier, but now with real numbers. The parameter w equals 2 is the one that makes this model match this data. A clean parabola. The bottom is at w equals 2. This plot is called a loss landscape, and finding the bottom is what training algorithms do. The difference is that real loss landscapes have millions of dimensions, not one. What happens if the data isn't perfectly clean? Now, no w gives 0 error, there's no perfect answer. But w equals 2.0 is still the best of the three. In the real world, data is always noisy. The model can't memorize it perfectly. It has to find the parameter values that are least wrong overall. That's actually a deep idea. Learning isn't about finding the right answer. It's about finding the least wrong one, given the data and the model you chose. Let's compress what we covered. AI is the field. Machine learning is the approach where models learn from data. A model is a parameterized function from inputs to outputs. Learning means adjusting parameters to reduce error on a task. Training is when parameters change. Inference is when we use the fixed model. We saw this with the simplest possible model: one parameter, one multiplication. The same structure scales to models with billions of parameters. The ideas don't change. The scale does. If any of these words still feel slippery, replay this episode before continuing. Every future episode builds on them. In episode 2, we turn this abstract idea of a model into geometry. We'll see what it means to draw a line that separates two classes. We'll see what a weighted sum actually looks like in space. And we'll hit the wall. There are patterns a single line cannot solve. That failure, the XOR problem, is the reason neural networks exist. And here's a question to chew on. If the simplest model is a line, what kind of shapes can we make by combining many lines? That's the intuition behind everything coming next.